Welcome to homework.
In part A, we're asked to show that the relation on the set of functions from the positive integers to the positive integers, such that the pair f and g belongs to this relation, if and only if f is big theta of g, is an equivalence relation. So, to prove this is an equivalence relation, let's prove it's reflexive. So let f be a function from the positive integers to the positive integers. And as f is large theta, we'll take k to be 1. Then we have that for all x greater than k with c equal to 1, we have that c times the absolute value of f of x. Well, this is simply going to be the absolute value of f of x. So this is going to be less than or equal to the absolute value of f of x. Clearly, this is going to be less than or equal to 1 times the absolute value of f of x, which is c times the absolute value of f of x. So this implies that f is big theta of f and therefore we have that relation R is reflexive since f is related to itself. Now to prove that R is symmetric, we're going to suppose that the pair FG is an R. This means that f is big theta of G. So then we have that for all x greater than k, for some non-zero constants c1, c2, and k, we have that c1 times the absolute value of g of x is less than or equal to absolute value of f of x, which is less than or equal to c2 times the absolute value of g of x. This is what being big theta of g means. Now let's take c1 prime to be 1 over c1. And let's take c2 prime to be 1 over c2. This is possible because c1 and c2 are both non-zero constants. Then we have for all x greater than k, by solving the above inequality, well, we have the absolute value of g of x over c1 prime is less than or equal to the absolute value of f of x, which is less than or equal to absolute value of g of x over c2 prime. And so we have that, in other words, c1 prime absolute value of f of x is going to be less than or equal to absolute value of g of x which is less than or equal to c2 prime times the absolute value of f of x. Actually, in reverse, we have, c2 prime times f of x. This is going to be less than or equal to g of x, which is less than or equal to c1 prime f of x. My mistake. So by big theta notation, we have that g is big theta of f. So it follows that g is related to f, and therefore that r is symmetric. Now to prove that r is transitive, suppose that f and g are related and that g and h are related. So this implies that f is big theta of g, and we have that g is big theta of h. So we have that for some non-zero constants c1 through c4, and k1 and k2, we have that c1 times the absolute value of g of x is less than or equal to absolute value of f of x, which is less than or equal to c2 times the absolute value of g of x for all x greater than k, and we have that c3 times the absolute value of h of x is less than or equal to the absolute value of g of x, which is less than or equal to c4 times the absolute value of h of x for all x greater than k. Well, this is k2, so that was k1 and this is k2. Now, combine these statements. Let c1 prime be c1 times c3. Follows that c1 prime is not 0 since c1 and c3 are both non-zero. c2 prime will be c2, c4, also non-zero since c2 and c4 are non-zero. And we'll take k to be the max of k1 and k2. Then follows that for all x greater than k, we have that c1 prime times the absolute value of h of x well, this is going to be the same as c1 times c3 times the absolute value of h of x, which we know is less than or equal to c1 times absolute value of g of x, which we know is less than or equal to the absolute value of f of x, which is less than or equal to c2 times the absolute value of g of x, which is less than or equal to c2 times c4 times the absolute value of h of x, which is equal to c2 prime absolute value of h of x. Therefore, it follows that f is big theta of h. So it follows that f is related to h, and therefore that r is transitive. Since r is reflexive, symmetric, and transitive, r is an equivalence relation. Now finally, in part B, we're asked to describe the equivalence class containing the function f of n equals n squared. So we're looking for all the functions that have the property that g is big theta of f, or vice versa. Where f of n is equal to n squared. So we have that the equivalence class of f with respect to r, this is going to be the set of all functions g such that g is big theta of f. This implies that this is the set of all functions g such that there exists non-zero c1, c2, and a k such that c1 absolute value of f of x is less than or equal to absolute value of g of x, which is less than or equal to c2 absolute value of f of x for all x greater than k. And substituting, we have that this is going to be the set of all functions g such that there exists constants c1, c2, and k such that c1 times absolute value of n squared, which is simply n squared, is less than or equal to the absolute value of g of x, which is less than or equal to c2 n squared. In particular, for all x greater than k.